Suppose we are working with this function and I have taken this partition of the codomain 0 to m. Now we will get one lower approximation and one upper approximation. This is the lower approximation and this is the upper approximation. Now we said that if I make this partition just anything, finer or whatever, and if I take supremum of all the total areas that I can get from the lower approximation and the infimum of all the things coming from above, then hopefully they will be same. In that case, I will say it is Lebesgue integrable. So the natural question is, what are the cases where the two things will really match? So the supremum from below will indeed equal the infimum from above. We of course had a very similar condition to check for Riemann integration, and there the answer turns out to be rather difficult to manage because the condition of Riemann integrability is difficult to express in terms of anything simpler. But in this case it turns out that this condition is very nice to write down, and the condition is a very natural one which also occurs in other contexts as well. To write down the condition, let this function be given the name f. So f is a function from ab to r. Say in this case it is between 0 to m. So the condition is whatever b you take in script b, you remember our script b, all the things for which we can define length, take its pre-image. The pre-image is also something for which we can define length. So if a set is measurable, its pre-image is also measurable. If your f satisfies this condition, then you will have equality here. Conversely, if you have equality, this must be satisfied. Now this condition is so very important that we have a name for it. We say that f is measurable. So whenever you give me any set in B, the pre-image must also be in B, script B. So if you think of all the elements of script B as good, it says that if you take any good set, its pre-image must again be a good set. So that's a nice property for F to have. And it turns out that this nice property, which is also nice in other contexts as well, and it's not a very strong condition, so to say, and this condition is enough to guarantee that these two things should be the same. So checking if something is Lebesgue integrable is not difficult, and in most cases we work with functions like this only. So you can say for all the functions that we'll be working with, we'll always have this condition that Lebesgue integral is well defined. Here is one little exercise for you just to get used to the concept of a function being measurable. I have given you a simple function of our familiar form, summation ci, indicator bix, where the ci's are real numbers and bi's are in R, any subset of R. Without loss of generality, you can assume that ci's are all distinct and bi's are all disjoint. The only condition that I have dropped here is that bi's are all measurable, that is bi's are in script B, and that is exactly where the problem lies. You have to check that Sx is measurable if and only if all the bi's are in script B. Very easy to check, just carefully writing down the definition is all that you have to do, but you have to prove both ways. If it is measurable, then all the bi's must be in script B. Conversely, if all the bi's are in script B, this must be measurable. Trying this direction from here to here would be, I think, easier.